Hello. So today we give, I'll try to explain you one more example. So the reason why I'm doing this is because up to now we considered a rather simple system which had the form like has a general form. So it was ODE with a singularity. So it was singular, or what singular means, non-Lipschitz. At just single point at the origin. So this is a nice set of examples which give some insight of what may happen in turbulence, especially about the spontaneous stochasticity effect. But certainly this system is very, very far from any fluid dynamics equations because, first of all, it's finite dimensional, so it's ordinary differential equations. Second is that the singularity is somewhat of different type. It's already included into the field in a sense. It does not appear naturally from the dynamic, and method B. Okay, so it does not appear naturally from the dynamics, and also it's just one single point. So certainly fluid dynamics is different. So today we consider example which is still solvable. This is very recent result. So it will be solvable example, which means that we can completely characterize the dynamics and see many properties of the solutions that tomorrow we'll discuss in more details in relation to Navier-Stokes Euler equations. Okay. So what should we change in the example for having somewhat better and closer to the fluid equations? For this, I'll just show you a few images from real turbulence, and then we understand what we need. So this is here. So this, let me change the cursor. So this here is Navier-Stokes equations, and let's see how turbulence occurs in a cup of coffee, for example. So what happens in a cup of coffee? So the coffee put milk, and then you see that it starts to creating very complex structures. So you see the structures as long as milk did not mix. So you really can follow this. This is what was told by Simon in his lecture. So this is this visual picture follows the Lagrangian, essentially the behavior of a scalar, of the density of the milk. So as long as it did not completely mix, you can see the flow. So just let's see it again. So you put milk, and then you see that some smaller and smaller structures appear until milk mixes so much that you don't see anymore what happens, but it still continues to happen. So it all continues to happen. So what essentially occurs qualitatively is that the behavior of turbulence is that you put a forcing, so you make a disturbance or inject energy in a physical language, so at a large scale. So you put milk or you mix your coffee with a spoon. So you do really large scale motion. And then out of the big vortices start to produce smaller vortices. These smaller vortices produce even smaller vortices, these even smaller, and so on. And in a developed turbulence, so in the limit when the viscosity goes to 0 or randomness goes to infinity, this is infinite process. So there is a transfer of motion from large scale to smaller scales. So this is what happens in turbulence, and this is what we want to follow, and this has to do with the scaling law. So just before doing this, I'd like to suggest you maybe to take a look at this turbulence webpage and encyclopedia. So this is a description of turbulence rather from mathematical physics or theoretical physics point of view. So this is another picture of what happens with turbulence, more in a kind of poetic way. So this is a quote from Jonathan Swift's poem, which was about poetry, but it equally well applies to turbulence. So naturalists observe a flea. So you see many fleas. The fleas has smaller fleas that on him prey, and these have smaller yet to bite them, and so proceed ad infinitum. So you see that there is a big. So in turbulence, this flea is a vortex. Let's say so. There are small vortices that feed from the bigger vortices, and the smaller vortices that feed from a medium vortices, and so on up to infinity. So somehow Jonathan Swift perfectly reproduced the modern vision of turbulence. And the interaction is of course two-sided. It's not just smaller vortices are feeded from the bigger vortices, but of course bigger vortices are also influenced from the side of the smaller vortices. So the interaction is two directions, from bigger to smaller size and from smaller to bigger size. And what we will see that actually there are two different physical phenomena which is related to this interaction. So one of them is transfer of energy, which exactly correspond to the interaction from bigger to smaller. And in today's example, we will see the opposite case is a spontaneous stochastic behavior, which is actually related to the interaction from smaller to bigger. So since they interact always both sides. So the interaction from bigger to smaller is responsible for transfer of energy, and from smaller to bigger is for the spontaneous stochasticity. Essentially, it's for the transfer of error. So this is so we today will try to consider a very specific example. So let's try to do that. So I will turn it off. Okay. So our model. So what we want to do, we want to reproduce multi-scale dynamics in a way which is not really, it's not really that we want to be close to the fluid dynamical equations, but we want to have a model which resembles some properties of fluid dynamics, which is multi-scale system. So it will be multi-scale model. At the same time, equations of fluid dynamics are very complicated, so there are no yet methods how you study this phenomenon for the fluid dynamics. So we can try to construct simpler equations in such a way that we can solve them. And then we learn what happens with this phenomenon from these small equations, and then we can think what happens in the original model. Okay, so we want to have a multiple scale, so we will proceed similar to the shell model. So we will take the first scale, L0, let's say 1, then there will be smaller scales. So remember that there should be many scales. So 1/2, The next scale will be 1/4, and so on. So this is exactly the picture we had. 1/8, and so on. So we have many scales, and at every scale something happened. So at every scale something happened, but suddenly the rotation in fluid dynamics, if you have a big scale, the typical time of rotation in a big scale is larger. So if it's the smaller scale, the rotation time, the period of rotation of a vortex will be every time smaller and smaller. So smaller the scale, smaller the time. So we can define times, and this we can also do arbitrarily because we just construct a qualitative model. So we put corresponding characteristic time, so we will call the turnover time. Turnover times. We'll just take the same. This is simplest solution. So tau n is equal ln. So each scale behaves with the characteristic times which are proportional to the scale, equal to the scale. So this is what we will do, and then immediately you can think of dynamics. So first we should think of the space-time. So the space-time so what will be the property of space-time? So we have scales. So we have scale 0. Then we will scale L1. And we'll scale L2. L3. So this will be a line which will correspond to the evolution at each scale. Everything is schematic. So this will be a direction of scale. So going low and low, we go to the smaller and smaller scale, and then we'll have a direction of time. But time, you see, time is, we can use discrete time because something important happens only at the turnover time. So we will say that this T0, so we will put nodes. So we will put node at 0 time, at turnover time, 2 turnover times, and so on. So that's its first scale. At the 0 scale, the L1 scale has turnover time which is half of it. So we have a node here in the middle, the same place in the middle, and the same place, and so on. Then the next scale, it's still twice smaller turnover time. Twice smaller turnover time in the next scale. And so on. I think this is the smallest I can plot. clear, no? Okay, we'll finish. Good. So this is what you see here is our space-time. This is our space-time. So the time is horizontal, and instead of space variable, we have just different scales. So now we give, to each node we give a variable. So each node we give a variable. So, for example, this the variable will be, this will be u1 of t. Here will be u2 of t, and so on. So the index will, so each variable will have, so the variables or speeds will have form un of t. Okay? So what means un of t? So in that case, n, let's put it here. So in that case, n and t, they belong to the n of t is such that n should be integer, 0 positive integer, and t, you see, for each integer, t should be integer number of 2 times. So this z plus, what I'm giving as z plus is z are non-negative integer numbers. So we have a space-time, and now we can define analog of turbulent flow on this space-time. So analog of turbulent flow. In order to have turbulent flow, we need. So we say that each node is will correspond to the state of the let's say vortex of size L0 at this corresponding time. And this will correspond to the small vortex at size L3 at different times. So we need to put variables which describe our dynamics of our vortex. This is also, we can do whatever we want because we are constructing the toy model. So what we do is we take un at every time is point on the two-dimensional torus. So point of the two-dimensional torus, it means that so what is two-dimensional torus? Two-dimensional torus is a set of points which are both considered modulo 1. So in other words, the two-dimensional torus is a square from 0 to 1 with operations that whenever you add or multiply numbers, whenever it goes outside the torus, you take it modulo 1, so you return to the torus. Good. So we have variables. So at each node we have a variable. And now we need, the last step is we need to write equations of motion. So we have space-time, we have variables, so we need the equation of motion, which means these interactions, like this fleece which bite each other. So we need to see how these variables will bite each other. And we will, there are two types of dynamics. So one type of dynamics is that you see the vortex, it moves from one time to another. So there will be some law of motion, some law how the vortex will change over the turnover time. So it makes one turnover time and it changes a little bit. Yeah, so these arrows will define turnover times. the changes of 10 over time, and I will show in a while what does this arrow mean. So this arrow will mean just a specific formula. So there are horizontal arrows which connect every two neighboring points. And then we also need to introduce interaction between different scales. So this corresponds to this fleece biting fleece of larger fleece, or vice versa, the larger fleece being influenced by the smaller fleece. So what we will do is we will only consider an interaction from smaller to the larger fleece. So from to the large. So whenever the large fleece will make one turn over time, it will feel some effect from a smaller one. And this will happen equally everywhere. So the last step is to understand what means an arrow. What means an arrow? So the arrow will mean Arnold map. So what is Arnold map? So let us introduce the Arnold map. Arnold cat map. Arnold cat. So Arnold cat map is a map from a torus to a torus, which is defined as so A of xy. So xy is a point on the torus. Must be to x plus y, x plus y. Model is model 1. So whenever you go outside, it's model 1. So we can draw this map. So what it does, so let's plot x and y, 0, 1, 1. So we are living in this square from 0 to 1. This is torus. So what it does? So it is. So we can check with the point 1, 1. Point 1, 1 is mapped to point 3, 2. So we can write point 2 and point 3. So what happens is that this vertex is mapped here, which automatically so then this vortex, which is 0, 1, 0, 1 is mapped to 1, 1. Is mapped here. So 0 stays in the same place, and then 0, 1, 0 is mapped to 1. So here. So what happens is that our square is mapped to such an elongated rectangular. So this is a map. So it takes square, maps to a rectangle, but then you should make it, you should put it back to the one, to the torus, taking this operation of modulo 1. So what it makes, it maps this. So this part. So you see it. This goes here. This stays at the place. This goes here. This goes here, and this goes here. So this is a map. This is how it makes what it does. But at the same time, there is a graphical representation, and graphical representation was made for the picture of cat. That's why this map was called cat map. So you can draw a cat. So this map will map it to, we will cut the cat into pieces. So somehow it will be something like, so it will stretch, you see it stretches the cat, and then cut into the pieces and put it back. So it will be like, it will be here. And so on. So this is a map, so it takes a cat and then cut into the pieces and stretches. Give them. Arnold was calling it soup of the cat. Okay. So this map is very nice. This map was very popular in dynamical system because it in a very simple way it incorporates many interesting properties. So the first, it's invertible. So whenever you do A, you can have A minus 1. Then it's also area preserving. So that's also a nice property. So whatever area you take, you map it the same area. Then it has two eigenvalues. One is alpha, which is 3 plus square root of 5 over 2, which is irrational. And another is minus 1 over alpha. So it is this map is hyperbolic. So what it does, it stretches every piece or any object you put, it will stretch it in one direction with the rate of alpha and compress with rate of 1 over alpha in another direction. So it's hyperbolic. So whenever whatever you put, it always stretches in one direction and compresses in another direction. And finally, it's ergodic. So I will not give a definition of what is ergodic, but it has many implications. One of them is that almost every orbit means that you take some point u, then take au, a square u, a cube u, and so to infinity. So whenever, for almost every point that you can take in a square, you will have some point u, then take a u, a square u, a cube u, and so to infinity. So whenever, for almost every point that you can take in a square, you will have some point u, then take a u, a square u, a cube u, and so to infinity. So whenever, for almost every point that you can take in a square, you will have some point u, then take a u, a square u, a cube u, and so the corresponding orbit is dense. So whatever point you take, and then you apply many times the Arnold map, it will go everywhere. So it will visit every place. Good. So now what we say is that every arrow is Arnold is A. Every arrow is A, and this gives us equation of motion. So what is equation of motion? If whenever you have the new value here, it is obtained from two sides. From the left, so from the previous state of this at the same scale, and from the influence of the smaller scale at the same time, at the same previous time. So the previous time, you remember that this interval is T1, is tau 1. So for every, so you can write equations of motion. Equations of motion. So the evolution such that un t plus tau n. So whenever you want to see what is at the next time, you should take Arnold map. So this is an arrow to the previous state. And the Arnold map to the previous state, but at a smaller scale. And smaller scale at n minus 1, plus 1. So that's equation of motion. So you see, essentially what it gives it for it gives the equation which every point the variable at every point is defined by the two variables on the left. This is defined of two variables on the left. This is defined of the two variables on the left. So every state is defined by two variables before, at earlier times. So this is what usually evolution does. So equations of evolution determine the state at every time by the state at previous times. So this is what we do. At previous times and just at the two scales, at the same scale and smaller scale. Same scale, smaller scale. So essentially we are almost done. So the last ingredient of our problem is initial condition. So we can give initial condition. So initial condition at time 0. So we can tell that un at 0 is some value. So for all n. And this gives us initial value problem. So we have initial value problem, which is the equation of motion at every scale and initial condition. So we have all the values on the left side, and we have a equation which determines every node in terms of the previous. Every node in terms of the previous. And we have this multi-scale structure of fluid dynamics, which tells you that the typical times at larger scales are larger. So in order you go to smaller scales, the typical times are smaller, typical times are smaller, typical times are smaller and smaller. So in terms of the symmetries, you can say that this system has a space-time scaling symmetry. So what it is it is for every. So what you can do is whenever you take the transformation un of t to un plus 1 t over 2. So whenever you have a solution, you can change scale and time, and it will be new solution. Yeah, so this is a transformation which is it's valid everywhere except for at the larger scale, because nothing comes to it. But yeah, okay. So this is a symmetry. So whenever you have one solution which solves this equation, so in other words, these equations, they are invariant under the change of under this transformation. So this is space-time scaling symmetry. So this just space-time scaling symmetry, which is symmetry of the equations of the ideal fluid dynamics. Okay, so now we try to solve this system. So what do we have? So we have this blue will be initial condition. So we have these numbers. We have these numbers. So at the moment we have these numbers, you immediately see that having these two values, we can use the equations of motion. And from these two values, we construct the value here. We put it in green. So this is first step dynamics. These two values give us the first step dynamics here. These two values give us first step dynamics here. So the values at the green points are uniquely defined. So solving initial value problem. So solving initial value problem, we find that there is a unique values of u and t at the, let's say, green set. So green set will be set of points, set of scales and times, where n is arbitrary, positive integer, and t is just one turn over time. So this is green set, which correspond to the points which just moved one turn over time from the beginning. Okay, and for the rest, it's much worse because you can see, so it would be, so we would have a unique solution everywhere else if going to the left, for example, take this point. So if you go to the left, in order to know value at this vertex, you need to have values at this vertex, two vertices. Then it means that we need values at these 4 and these 2. So this, and this. And this determined by this, and so on. So essentially, you need to go, in order to understand what is the value here, you should go along all possible trajectories that go on to the left direction until they reach the time 0. And then at time 0, you know what is the value. So you take this value and then propagate back to the point. So this is how you, in principle, may determine the value at every point. So you should just take the left values, the next left, and so on. So this would be very nice, but this does not work This does not work because there are trajectories which do not reach the left time zero axis. Because you imagine, so if you from here, if you always go in a diagonal, you see you never come to the left axis. So you just see because you go half time, quarter time, eighth time, and so on, and you see that this will sum up to 1. It cannot sum up to 2. So there are many trajectories that actually do not lead to the initial condition, and this is a source of non-uniqueness. And exactly what we can do is that we can write this expression in a different way. So here we will take into account that A is invertible. So we can invert A, so we can multiply by A minus. And you see we multiply by A minus, and then what we will do is we will express un plus 1 for the others. So what I will write is, this is a consequence of the equation of motion. So un plus 1t will be A minus 1 un t plus tn, tau n, minus un t. This modulo. So this is just the same equation of motion, but written just slightly transformed. So what this means? So remember, so in original picture, we had, so this was un plus 1 t plus tau n. This is, no, un. This is un t. This is un plus 1 t. So in original picture, we have this relation. So this relation which expresses the variable at forward time with respect to the variable at previous times. So this expression does a different thing. It expresses lower point at smaller scale through two terms. So what it does, from here it will go as A minus 1, and here it will go just as minus 1. So you see, if you want to obtain this term in terms of the upper two, you multiply the first by minus 1 and the second by A minus 1. So this is just transforming the triangle. So what we can do with this? What we can do is, it turns out that that we can split all the points into two classes. So one class will be red one. So it will be this point. Then it will be. So these are all points on the first line after the green one, and then these are all points on the odd number of the de novo times. So we call them red. These are red points. And now what we do? So now what you can see is that we can just go triangle by triangle. So for example here. So this is a red set. So let's just write what is a red set. So we have a red set. So a red set is is the sum other all points on the first line. So 0, j plus 2, starting from 2. And all even points or odd number points on other lines. So starting from the second line, we're taking all odd points starting from number 3. So we have a set of red points, and we can actually, it turns out that we can put any number here. So let us assume that we put just arbitrary number here and try to see whether it will work or not. So let's put just red point is just any value on the torus, any value. So it turned out that it works because, for example, look at this triangle. This triangle has, we know what is in green point, and we assigned arbitrary number to the red point. So it means that here it's uniquely defined by that formula. Then having this number, we have this red point, so we know what is defined here, and in the same number we know what is defined here. And so on. So you can just check that whenever you assign every red point with some number, which is arbitrary, all the remaining vertices are uniquely defined. So the last set, which is I was calling it black set, but I don't have a black chalk. So black, it's a remaining set, which is you see, which are even turnover times variables starting from the second line. So it's you can write it exactly as. So you start from the first scale, and you go only to even turnover time starting from the second. So the theorem. So the theorem that we essentially proved by looking at the triangulars is that there is an infinite and actually uncountable, because we put arbitrary real numbers, so infinite number of solutions to the initial value problem. So the initial value problem is what we wrote before. It's equation of motion which determine the evolution of the variable at each scale and given initial condition at time 0. So despite we have equation of motion which define the evolution at every scale. So at every scale we know how we evolve because the value at the next time is just sum of the values at the previous times multiplied by the Arnold cat map. Yeah, and given initial condition, we still have infinitely many solutions. And these infinitely many solutions, so each are fully classified. So each solution depends is determined by initial conditions and arbitrary values u and t at this red set. So we completely classified all possible solutions. They're strongly non-unique. So this is a system which resembles fluid dynamics. It has the same symmetry. And it has the same philosophy, because it has many scales. At each scale, we have dynamic at different time steps, turnover times. All deterministic initial conditions are given, and you still have infinitely many solutions. And this is very, very strong non-uniqueness, because you can put whatever values at every red point, and all the rest will be defined uniquely then. But you see, so every second point, half of the variables are arbitrarily defined. So this is how strong is the non-uniqueness. And you will see that tomorrow we will see that actually this property transfers to the equations of fluid dynamics. So the effects of fluid dynamics are also very, very strongly non-unique if you consider ideal fluid. So the equations without viscosity. So this is a equation in the limit of when you put viscosity to 0, which is exactly the limiting value of our interest for the turbulence. So okay, let's make a short interval, 5 minutes. And then we'll continue. So we have strongly non-unique solutions, and actually there is more than that. There is more than that because there are some quite funny solutions which look very strange, and then you can even think that our model is just not well done, but actually this is exactly the analog of the weak solutions that were found in the earlier equations for the incompressible fluid. So this was rather interesting finding from some two decades ago that led to many developments in pure mathematics, but this we'll talk tomorrow. So the solution is like this. So just let us draw again this our lattice, but I will draw longer times. And then you always divide, on a lower scale you always divide by half. On a lower scale you divide by half again, and so on. This is how our space-time is created. So let's put 0 initial condition. 0, 0, 0, 0. So let's put absolutely 0 initial condition, and that means that automatically it will be 0 here, right? So it will be 0 here, 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 which is a green set. But we know that at the red points, the values are arbitrary. So we will take everywhere 0 except for some of the red points, and some of the red points are the ones which are so we take this red point, this red point, you can still have this, this, this. So what we do is, first of all, we will separate, we'll put 2 vertical lines. So one vertical line will be here. Another vertical line will put, so one vertical line will be put at time 1. Another vertical line will be put at time 4. So at the time before 1, everything is 0. And 0 is agrees with the equation of motion, right? So, and with the initial condition. And we will put everything at 0 also at time 4 and at all larger times. So here everything is 0, and here everything is 0. But now we put red points to be arbitrarily. So these are arbitrary points, arbitrary non-zero values. Arbitrary values. So what you can check is that it will still be 0 here because it. So you see this 0, it will be still 0 here. This will be still 0 here. Okay. So, but now what you can see is that there will appear some non-zero values. So where it is? So this here 0 and something. So here will be some non-zero value. Then here it's also non-zero value. Here is non-zero value. And so on. Then it will be, these 2 values give something non-zero here. automatically this will come from this to where it's not 0. So you will see that all these values are non-zero, but uniquely defined. So essentially what you can see, but these values never cross number 1. They never cross number 1, time 1, and never cross time 4. So what we see is that we have infinitely many solutions which satisfy 0 initial conditions. So this solution is what's called have a compact support in time. Compact support in time means that we had a completely 0 evolution, so nothing was moving. Then out of nothing, something started to move. And then at that moment, it stopped moving and it was 0 again. And also there is infinite number of such solutions which are called wild solutions. So wild because they are coming out of nothing. So there is a 0 initial condition, so nothing, and 0 initial condition by in a reasonable situation should continue to be 0. So if you have a liquid which doesn't move, it should not move at larger times. But there are solutions which suddenly start to move and stop moving. And it turns out that this is exactly the situation which you can have in weak solutions for Euler equations for the ideal fluid. So there are rigorous results that showing that such solutions exist. Okay, so the next our next step. So we have infinitely many solutions, and this is the trouble. So the next step, what to do is we already know what to do. We need to make a regularization. So regularization in regularization. Let me see. So regularization in the case of ODEs, what we were doing, we were changing the field near 0. In fluid dynamics, we put the viscous term, so it's a viscosity. And here we will do something similar to fluid dynamics. So what viscous term does is that when you have smaller and smaller and smaller scales activated, so what happens with the viscosity at a certain level, the motion is stopped by viscosity. So at a certain very small scale, you already don't have any motion. So everything becomes smooth and nicely behaved from certain scale on because of viscosity. And we can do exactly the same, even much simpler in our system. So what we will do, we take a regularized system. So we define a regularized system. So choose any number n, so integer positive number n. And n will give us a scale at which we regularize. So all what we do by regularization is that we say that un t are identically 0 for n bigger than n. So what we do is that you take a certain regularized scale Ln and just set everything below 0. by force. So this is regularized system. So you just put everything, so you consider the same dynamic up to scale Ln, satisfying initial condition, and just say that below everything will be 0. And this is somewhat in spirit of the viscosity, because viscosity in turbulence also defined a certain scale, which is called Kolmogorov scale. So below the scale, the motion is strongly suppressed by viscous terms. So here, this suppression will be extreme. We just say it's 0. Okay? So whenever it's 0, it means that our space is now, our scales are now finite dimensional. So we don't have anything below. We don't have anything below. And now, whenever you want to compute value at every point, so you have to go to previous points, for previous points, and so on. So you have to go along all the arrows backwards. So whenever this line will lead you to the initial condition, you should take this initial condition. But whenever this line leads you to the regularized level, n capital, you take 0. So whenever from below, you take 0. So when you go below this level, you automatically 0. So now you automatically uniquely defined. Yeah? So automatically initial value problem possesses a unique solution. So there is a unique solution, and we can call it Un of t, and we will put superscript capital N, which tell you that this is a solution regularized at capital N. So certainly this solution depends on a capital N. So for each capital N, so at each level where we regularize, we have different solutions. So we can also define implicit limit. So implicit limit is a limit in which viscosity goes to 0. Here we don't have viscosity, but we know that analog of the viscosity going to 0 is a regularization scale going to infinity. So it's implicit limit, or analogously Reynolds going to infinity limit. So in our model, it corresponds to n going to infinity. So now the question. Do we have a limit of the solution? So does it converge or not? So certainly in some cases it converges. So in the, for example, it converges in the situation when initial condition is 0. So whenever all initial condition is 0, we never can have this situation of wild solution. If initial condition is 0 and you have all zeros below, it's everywhere 0. So, for example, so if Un at time 0 is 0 for all n, so then all regularized solutions are automatically 0. And then it means that there is trivially there is a limit. So it gives you a solution which is 0. Yeah, so somehow in the case of at least the regularization procedure, does its job in this case. So it removes all white solutions. So white solution is just an artifact of the construction, which is, let's say, to which we give too much freedom. So we say that, so in the initial value problem, we only say that we have to satisfy all these relations, initial conditions. This gives us too much freedom because it gives us wild solutions. So whenever you regularize and take regulation limit, this freedom disappears. So we have just one limiting solution, somewhat in the spirit of Burger's equation. But this is not true in general. So not any initial condition is like that. And that leads us to the next theorem, which we can prove. So first, before proving the theorem, I'll give you the result from a functional analysis. Which tells you that for any initial condition, so this is results like theorem from functional analysis. So for any initial condition, there exists a sequence. So you can choose sequence of the regularization scales going to infinity, such that the limit exists. So this limit converges for all n and t. So at all vertices it converges to a solution u and t of original ideal, so not regularized problem. This theorem from functional analysis doesn't have to do with any dynamics. It's just based on some compactness property, which is telling that whenever a sequence of such numbers, which are labeled by capital N, you can have accumulation points, which means that you can find sequence of capital N's such that this regularized solution will converge to the ideal solution at all points at the same time. So we have this convergence, which somehow, first of all, it is exactly which we, in a sense, we want. So we want that the physical solution of the ideal system in the limit of developed turbulence limit, the limits of inviscid limit, it converges to some solution of the ideal problem. So, and this tells you that yes, you can do this, at least for the subsequence. And this is similar to what happens also in the fluid dynamical equation. So you can prove that there is a convergence in different situations. But the next result is what we expect but do not have but still cannot prove for the fluid dynamics. And in fact, this result tells you that this does not solve the problem at all, because the limiting solution only makes sense if the limit does not depend on subsequence. But there can be different subsequences going to different limits. And it means that actually this regularization procedure didn't work. So this is the theorem. So the next theorem is the following. So consider initial condition So we'll take specific initial condition for which it is convenient to make a proof, but actually it's just an example. So consider initial condition u and 0 equal to the same number, a, for all. So it's on a torus, right? So for same point on the torus for all n. So what we did is we put initial condition. As initial condition, we put exactly the same number, the same vector, everywhere. So we put the initial condition the same, and then now we take a regularization limit. So the theorem states that then for almost every a on a torus, so almost every number every value you put, there exists infinite, and in fact uncountably infinite, number of different solutions obtained as a subsequence limit n 1 and 2 and 3 and so on. So it tells you that for these initial conditions you can put almost any value of a, and then you will have infinitely many different subsequences which give you different solutions. Okay? And let us prove it. So how we prove? So how we prove? We take what we will do is that let us directly compute the value here. So what is the value here? So value here comes from initial condition at the same level. It comes also from initial condition at the second level. It also comes from initial condition on the other level, but through different passes. So you see here you can make two passes. Here you can also make second pass, and so on. So we can just directly compute what is here by knowing the initial condition for the regularized problem. And let us do it directly. So we compute U0 at time 2. So what it is? So let's just go from different point to point. So this initial condition, it comes after 2 steps. So this is equal a square 2 times Arnold map, but applied to U0 initial condition. Then for the second step, for the second level, it comes from 2 Arnold maps for this sequence of 3 Arnold maps for the lower sequence. So it will be a square plus a cube U10. So remember, so here we have initial condition U00. Here we take initial condition U10, U20, U30, and so on. So now this initial condition comes either from this sequence, which is which are 3 errors, or from this sequence, which are 4 errors. And so on. So you can directly get, and this continues until, this is not infinite, because it should be stopped at the level n capital, because there is nothing below, all is 0. So you can just write what it is. So you can see that this should be A2 U00, and this becomes a sum. So you can put this matrix out, and this will become a sum from n equal 1 to n capital. So this is where it stops. an un0. Okay, everything is modulo 1 always. But now you see we take initial condition everywhere to be a. So this becomes a square a plus a plus a square. Then it becomes a sum a. And this sum we know what it is. So this sum is remember, it's essentially like, it's a matrix, but since it's invertible, you can sum this polynomial as just as 4 numbers. So it's a minus I minus 1 times a n plus 1 minus a. So remember this formula. So then this becomes, so finally, we write that U0, U0n, so this is n, no? Time 2 is so we define a matrix B out of this one. So B will be a square so this is what? This is a minus I minus 1. Then it will become this is a minus let's do the next step. So it will be a square minus this by this by this, so it will become minus by square u a plus, so it will become a square A minus I minus 1 A that's it? Yeah. No. What we do with this. So it's, in other words, it's A minus I minus 1. Okay. So it's A from here and 1A from here. So let's keep the first term. So here it will be 1A from A squared by taking A from here and from here. Then it will be I plus A from here, A minus I from here, and then this term by A. So what will be left is AN minus 1 minus identity A. Okay. So what we do next is we call this B. So we call this B. So the result will be that U0 regularized at n at time t will be A squared A minus B. So A squared minus B A. And then this term B AN. So plus B ANA. Modulo 1. So where B is this matrix. So B is nice invertible matrix. Okay, so essentially what we did, we just computed what is here explicitly in terms of initial condition for the regularized problem. So the solution is unique and we just computed it directly. So the next step is the following. So the next level is the following. So first, use ergodicity. Let us use ergodicity. Of Arnold's cat of A. So using ergodicity, we know that for almost every A, the orbit which is given by A square A, and so on, is dense in the torus. So take this A. Take this A. The next, for any C on the torus, choose B such that A square minus BA plus BB equals this C. So since B is an invertible matrix, this is unique B. So there is a unique value B that for every given C, you take a unique B which takes this value. So we took A from ergodicity, we took C arbitrarily, and took B from this equation. So this is modulo 1. Everything always modulo 1. So we're always on a torus. So then, since orbit is dense, we can choose a subsequence which converges to any points we want. So since the orbit is dense, so since this A square A, and so on is dense, there exists a subsequence which converge to arbitrary point, in particular to that B. Which is the limit converges to B. So we just took subsequence which converges to B. So then we can just try we can compute now what will be the limit of the U0 at point 2. Then we can compute the limit along this subsequence of U and I and T. So what it will be? It will be, we just substitute that expression. So it will be limit of, first it will be A square minus BA. Which does not depend on n. And the next part depends on n, plus B A and I, A. But now we can take limit. The first part does not depend on at all on n, so we just keep it. And the second part we know converges to B. And this, by definition, we know it's C, which is arbitrary. So we found that we can find a subsequence. We can find a subsequence of regularization scales n. So we found a subsequence and 1 and 2 and 3 and so on, such that at least here we have convergence. At least at one point we have convergence. At point 2, so it's a 0 and 2 is arbitrary number given number. So whatever you want, you can arrange the subsequence so that value will converge to that value. But then, just as I said before, from function analysis, we know that we can choose a subsequence. Subsequence, so it means that it will be n I1, n I1, n I2, n I3. So just choosing some of these values, but still such that they go to infinity. And this subsequence will converge everywhere. That there is a limit of j goes to infinity of un n ij at every t. So it converges to some solution t at all now points. So in the first, in the construction, we considered convergence as just n equals 0, time equals 2. But choosing subsequence, we guarantee convergence everywhere. But we guarantee convergence everywhere, keeping this value. Yeah, because at that point, it will converge to the same value because it's a subsequence. Which automatically means that we proved that we can always choose a subsequence such that it will converge to the solution at every point and having arbitrary given number here. So this is exactly proves the theorem because for almost every A, we arranged an infinite number of different limiting solutions obtained at the subsequence limit. So that's our result. So similarly to the expectation of fluid in the developed turbulence, that we have a uniquely defined regularized solution, like solution of Navier-Stokes, and we can take implicit limit by sending Reynolds number to infinity or viscosity to 0. The solution, in principle, should exist along subsequences, but different subsequences give different limits. And in this example, we completely reproduce the situation, but in a provable way. So we can prove that not only there are different limits, but there is uncountable number of these different limits. So there is no, so it means that in the regularization procedure, we just put in the viscosity alone is not sufficient to understand the problem of the limit, so the developed turbulence. So there should be something extra that we have to put in the formulation, and tomorrow we will see this. So we will actually add noise, and we will see that then the limit is well defined, it's unique, and it gives spontaneous stochastic solution, which we can find. So okay, so let's stop for today. Thank you.